Greetings. Today we'll be discussing about Castiglione-First theorem. According to Castiglione-First theorem, when a beam or a truss is subjected to any load system, the deflection at any point R is given by the partial differential coefficient of the total strain energy stored with respect to the force PR acting at the point R in the direction in which the deflection is desired. The statement says that if one is interested to know about the deflection in a particular direction at a particular location, it can be obtained by taking partial differential coefficient, the partial differentiation of the total stored energy with respect to the load at that particular point. Let's put this one in a mathematical concept. Let a structure AB carrying a load system P1, P2, P3, P4, PR and Pn as shown in the figure here. The beam is subjected to n number of loadings, and the load which has been shown in red color mark, this is the point of interest. The load corresponding to this is PR and the location is Rnth location. If I want to know the deflection at this Rnth location or any other point, simply what I can do, suppose I have taken a y1 as a deflection at the point P1, then I can write y1 is equals to partial differential equation differentiation of strain energy stored divided by with respect to the load P1. So dou u upon dou P will be the the relation from which we can obtain the deflection of that particular point under that particular loading. Similarly, if I want to know the deflection for the loading for the load P2, then I can get y2 is equals to dou u upon dou P2. Then similar way I will have y3 is equals to dou u upon dou P3. Then at y4 we can have dou u upon dou P4, and at rth location I will have dou u upon dou PR. Okay, now let us try to have exact solution for this, a proof for this. For that, let us consider again a system and a particular load here. The PR is the load under interest at a point R location. Let us say this load is going to create a downward deflection of magnitude YR. So YR be the deflection at the point R. I am interested to know what is the value of this YR. For that, W is the work done by external force on the given by the external force here. Then Wi be the corresponding strain energy stored in the member. As we know that We equals to Wi means work done by external force equals to the total strain energy stored, that is the energy stored during the deformation of the body. Now, extending this concept, let load PR acting on the point R increase by a small amount delta PR. This load has been increased with a small amount delta PR, and that's why let load delta YR act let deflection, should be deflection delta YR acting at the point R, means there is an incremental displacement here due to increment in the force at that particular location. Then what I can get, work done is equals to work done due to this incremental load will be 1/2 of delta PR into delta YR. If I say about the total work done here, so actually external work done was WE. Due to increment in the work done, again the increment in the load, there is again additional work done on this system, that will be delta PR into delta YR. Okay, so here the incremental load is going to act, causing the further deflection in the beam. Okay, that's why the total internal work done will be equals to, we can say Wi plus delta Wi. Means here it is going to be increment in the strain energy stored by the body due to work done by increment in the force. That's why if we say these two things should be equal, that is external work done should be equals to the total strain energy stored by the body, then in that case we can write delta PR into delta YR is equals to delta Wi, because We and Wi, if when you equate, these are the having the same magnitude, same value, that's why they will get cancelled. What remains here, delta PR into delta YR, which is equals to delta Wi. If I rearrange this equation, what I will get, delta YR is equals to delta Wi divided by delta PR. Means here increment in the deflection is equals to increment in the load versus increment in the stored energy. Okay, so here what I will do, I will take a partial differentiation, or I will say its variation with reference to increment in the load at that particular location, what the statement wants to say in theoretical concept. This is the justifying proof for the Castiglione-Force theorem. Now we'll move towards the numerical to understand this concept in detail. The numerical 2, numerical 1 we have done in previous lecture. Numerical 2, find the deflection at a free end of a cantilever carrying a concentrated load at the free end. Assume flexural rigidity as a constant. So we have solved this numerical with the help of strain energy concept. Now we are going to solve this with reference to the what we can say your Castiglione-Force theorem. So a cantilever beam is given to us having end A and B. At end B there is a load P kilonewton. P kilonewton is going to act. The span of the beam is L. Due to this, there may be chances that deflection may occur in the vertical downward direction amounting value diabar. And I am interested to know what is the total diabar the deflection observed by the beam under the application of this load. So it will be, let us consider a section xx at a distance x from the point load. At this section xx, the moment at that section will be equal to p into x, is p multiplied by the perpendicular distance, and it will bear a negative sign because the section is towards the left hand side, and the sign convention for clockwise will then change to anti-clockwise. Now we know that strain energy Wi, U is equals to total work done, internal work done Wi, which is given as 0 to L P m square upon 2 EI dx in case of flexural forces. That's why we, after substituting the moment value, we can get here P square x square divided by 2I into dx. Now from this equation, if I integrate the things, it will become x cube by 3. X cube by 3 comes in the coefficient, 2 into 3 becomes 6. P square and L cube divided by 6. After doing the integration, I will get this value. Total internal work done equals to P square L square upon 6 here. But what the Castiglione-Force theorem says, if I want to, I am interested to have a deflection at this particular point, what I will do? I will integrate this. I will derivate the total strain energy stored in a body with reference to the load, with respect to the load here. That's why diabar will be equal to dou Wi divided by dou P. Dou Wi is nothing but the partial derivative of strain energy stored divided by dou P, increment in the load. So this will result into diabar equals to 2P, means here derivative P is variable now, 2P. The derivative of P square will be 2P and L cube become constant divided by 2EI. I have taken outside as a 2EI into 3. Means 6 has been replaced as a 2 into 3. So what will happen? This 2 coefficient get cancelled. What remains here? PL cube divided by 3I. This is the total deflection which is observed by the beam under the application of load at its free end. Okay. So this is the application of the Castiglione-Force theorem with towards the cantilever beam. Now let us have one more numerical related to that. Find the deflection of a beam carrying a concentrated load as shown in figure. Assume flexural rigidity as uniform. Here the simply supported is beam given to us. The point load which is applied on the beam is eccentric. It has a projection of A from the left hand side and B from the right hand side. I am interested to know what is the deflection caused by this force in vertical downward direction. For this case, what I will do, I will put the two, I will apply the equilibrium equation at both the end and try to get the reactive forces here. So when we will apply summation of Fy equals to 0, summation of M equals to 0, because it's now here coplanar force system and only the vertical forces are there. The one equation will get valid, only two equilibrium equation will get valid here. Okay, from the first equation, summation of Fy equals to 0, we get Ra plus Rb equals to P. Ra and Rb, they are going upward, that's why they will have positive sign. Minus of P, P on left hand side goes, it becomes Ra plus Rb equals to 2. If I consider first equilibrium equation with reference to y-axis, summation of forces in y-axis, I am getting a relation. Similarly, I will consider the second equilibrium equation by taking moment about the point A. The moment summation of moment about the point A will be equals to PA into P into A, means this will be the perpendicular distance with reference to the joint A. P into A, the product will be there, minus RB into L. RB into L. RB into perpendicular distance is L, and it is going to be in anti-clockwise direction. That's why equals to L, and this equals to 0. Then what relation we can get? RB equals to PA by L. So the value of RB is found out to be PA by L. If I back substitute this value in the first equation, Ra plus Rb equals to P, then I will get Ra is equals to P into L minus A divided by L. L minus A is nothing but the projection B. That's why you can say RA is equals to PB into L. Now what I will do, I will have two cross section, one just right of the point load and one just left of the point load, so as to have total variation of the deflection along the span. So when we say I am going to take a moment on both the side, both right and left side. So I will get moment along 1 to 1 section. Let us say this section 1 to 1 is towards left hand side. The moment 1 to 1, it will be RA into X, RA into X, which is nothing but PB into L divided by X. This is the replacement of the value of RA. Similarly, if I take a moment about the section 2 to, then it will be RB into X, that is PA into L divided by X. RB, I have replaced the value of RB here, PA into L into X. Now I will work out for the total strain energy of this particular beam. Then it will be strain energy stored with reference to first moment, and the strain energy stored with the second moment. So here it will be P square, means here it will become P square, here M square is given, then U1 becomes here P square B square X square divided by 2EI L square. In the second case, it becomes P square A square X square divided by 2EI by L square. What I have done, I have simply substituted the value of the moments here, and I try to evaluate this U1 and U2, and then I will add this to get the total strain energy stored by that particular beam under the action of point load P. Now when we say U1 plus U2 is equals to U, then U is equals to integration of this first term and the second terms I have put here, and then I try to integrate it. What is the P square B square will be constant here, and the integration of X will become X cube, which will range from the first span 0 to A. Similarly, for the second case, it will range from the second span 0 to B. If I substitute the individual values here, what I will get P square A square B square A plus B divided by 6EI L square. Means here I will get the relationship by taking something common one side, and put this relationship in a rearranged pattern. Then what I will get, U is equals to P square A square B square L plus A plus B is nothing but L. So what will happen, one power of L will get cancelled. What will get total stored energy stored is equals to P square A square B square divided by 6EI L. Now I am interested to know what is the deflection at that point. So what I will do, I will take a partial derivative of this stored energy with reference to load under reference. That will be dou Wi divided by dou P. The above will be equals to, now I will take a derivative of this. P becomes variable and other things are constant. That's why P square derivative will be 2P A square B square divided by 6EIL. 2 and 6 are there in numerator denominator, which can be rearranged as a P into A square B square divided by 3EI. This is the total deflection which is observed by a beam under the action of the point load. Now with this I will end the lectures related to basics of structural analysis. In upcoming lectures we will deal with the part of analysis of determinate and indeterminate trusses. Till that, stay at home, be safe, be healthy.